Polyzwitterions, surface immobilization, physical properties, and structure property relationships. Polyzwitterions are a distinctive class of amphilytic polymers characterized by the presence of equal numbers of cationic and anionic groups within individual repeat units. This intrinsic charge neutrality leads to unique physiochemical behaviors, including strong hydration, anti-polyelectrolyte effects, and remarkable resistance to biofouling. These properties have driven extensive research into their use in biomedical surface engineering and advanced materials. This video report provides a comprehensive overview of polyzwitterions, focusing on surface immobilization strategies, fundamental physical properties, and key structure property relationships that govern their performance in aqueous and biological environments. Polyzwitterions are polymers containing covalently linked positive and negative charges within the same repeat unit, typically forming inner salts. Common functional motifs include ammonium cations paired with sulfonate, phosphate, or carboxylate anions, yielding sulfobetanes, phosphobetanes, and carboxybetanes, respectively. Unlike polyamphylites, where oppositely charged groups are randomly distributed along the polymer chain, polyzwitterions exhibit precise local charge compensation. This structural feature results in distinct physiochemical properties, particularly in aqueous media. One notable phenomenon is the anti-polyelectrolyte effect, where polymer chains collapse in low ionic strength environments due to strong intra- and intermolecular ion pairing. Upon the addition of salt, these ion pairs are disrupted, leading to chain expansion and increased solubility. The strong hydration and charge neutrality of polyzwitterions contribute to their exceptional resistance to nonspecific interactions with biomolecules, making them highly attractive for biomedical and anti-fouling applications. Surface immobilization of polyzwitterions. For most practical applications, polyzwitterions are employed as surface coatings rather than bulk materials. In such systems, the underlying substrate provides mechanical stability, while the polyzwitterionic layer governs interfacial properties. Covalent attachment is generally required to ensure coating stability, particularly in biomedical contexts where regulatory compliance is critical. Surface activation techniques, including plasma treatment, UV irradiation, and chemical functionalization, are often necessary to introduce reactive groups. Subsequent covalent attachment can be achieved either through linker molecules or intrinsic functional groups within the polymer. Surface architectures. Self-assembled monolayers, SAMs. Self-assembled monolayers are formed by the adsorption of small zwitterionic molecules bearing surface reactive groups such as thiols or silanes. These systems produce highly ordered, nanometer-scale coatings with well-defined molecular orientation. However, their limited thickness restricts mechanical robustness and long-term durability. Polymer brushes. Polymer brushes consist of polymer chains tethered at one end to a surface. Two primary fabrication methods are used. Grafting to preformed polymers are attached to the surface. This approach is limited by steric hindrance, resulting in relatively low grafting densities. Grafting from surface-initiated polymerization enables higher grafting densities and thicker films due to reduced steric constraints during chain growth. Brush architectures exhibit enhanced hydration and superior resistance to biofouling compared to monolayers. Cross-linked polymer networks. Cross-linked polyzwitterionic networks, or hydrogels, are formed either from preformed polymers with cross-linkable groups or via in situ polymerization. These systems are characterized by their mesh size and cross-link density. When attached to surfaces, swelling is restricted to the direction normal to the substrate, leading to anisotropic swelling behavior. Physis-sorption versus chemisorption. While non-covalent adsorption, physisorption, can produce stable coatings under certain conditions, these layers are often susceptible to desorption in physiological environments. Covalent immobilization, chemisorption, is therefore preferred for applications requiring long-term stability and resistance to mechanical or chemical stress. Surface characterization. Achieving uniform surface coverage is critical, as defects can compromise anti-fouling performance and lead to misleading biological responses. Techniques such as atomic force microscopy, AFM, scanning electron microscopy, SEM, and ellipsometry are commonly used to assess surface morphology, thickness, and uniformity. Physical properties of polyzwitterions. Hydration and anti-fouling behavior. Polyzwitterions exhibit strong hydration due to electrostatically bound water molecules surrounding the ionic groups. This results in low interfacial energy with water, preservation of the hydrogen bonding network, resistance to the adsorption of proteins, bacteria, and cells. The anti-fouling behavior arises from a combination of enthalpic penalties associated with dehydration and entropic constraints related to polymer chain deformation. Anti-polyelectrolyte effect. In salt-free aqueous environments, strong ion pairing between oppositely charged groups leads to polymer chain collapse and reduced solubility. Increasing ionic strength screens electrostatic interactions, resulting in chain expansion and enhanced solubility. This behavior plays a key role in determining swelling and interfacial properties. Stimuli responsiveness. Polyzwitterions respond to various environmental stimuli. Ionic strength modulates chain conformation via electrostatic screening. pH influences ionization state, particularly in carboxybutane systems. Temperature. Certain systems exhibit upper critical solution temperature, UCST, behavior. These responses enable tunable material properties for adaptive applications. Swelling behavior. Swelling of polyzwitterionic networks depends strongly on ionic conditions. In low salt environments, collapsed conformations dominate, whereas higher ionic strength promotes swelling due to charge screening. Surface-attached systems exhibit directional swelling, influencing thickness and permeability. Structure property relationships. Ionic functional groups. The chemical nature of ionic groups determines stability and responsiveness. Sulfonate and phosphate groups, strong acids, remain ionized across broad pH ranges. Carboxylate groups, weak acids, exhibit pH-dependent ionization. Consequently, sulfobutanes and phosphobetanes generally provide greater stability under physiological conditions. Charge separation and spacer length. The distance between oppositely charged groups influences dipole strength, hydrophobicity, and acidity constants, pKa. Increasing spacer length typically reduces electrostatic interaction strength and enhances hydrophobic character. Polymer backbone effects. Backbone chemistry affects mechanical properties, flexibility, and chemical stability. Metaacrylate-based systems are widely studied, while alternative backbones such as ring-opening metathesis polymerization, ROMP, derived polymers offer enhanced structural control but may introduce additional chemical reactivity. Side chain functionalization. Side chain modifications play a critical role in tuning surface properties. Incorporation of hydrophilic groups, e.g., ethylene glycol units, enhances wettability and anti-fouling behavior, whereas hydrophobic or fluorinated groups increase surface hydrophobicity. Dipole orientation. The spatial arrangement of charged groups within the repeat unit influences polymer conformation and sensitivity to ionic strength. Variations in dipole orientation can lead to significant differences in solution behavior and interfacial properties. pH-dependent charge states. In systems containing ionizable groups, environmental pH can alter the balance between cationic, anionic, and zwitterionic states. These transitions affect swelling, solubility, and intermolecular interactions, enabling pH-responsive behavior. Applications and emerging trends. Polyzwitterions are widely explored in biomedical and technological applications due to their unique interfacial properties. Key applications include anti-fouling coatings for implants and medical devices, drug delivery systems, biosensors and diagnostic interfaces, membrane technologies for controlled transport, conductive and bioelectronic materials. Recent studies suggest that polyzwitterions can exhibit controlled bioactivity through stimulus-responsive mechanisms, challenging the traditional view of these materials as purely biopassive. In conclusion, polyzwitterions represent a versatile and highly tunable class of polymers with exceptional interfacial properties. Their intrinsic charge neutrality, strong hydration, and responsiveness to environmental stimuli underpin their widespread applicability in advanced materials and biomedical engineering. Continued advances in polymer synthesis and surface engineering are expected to further expand their functional scope and enable precise control over structure-property relationships.